Benvenuti a tutti, contro numero 119 del Jug Milano. Questa sera abbiamo uno speaker internazionale e siamo felici di averlo con noi. Giusto brevemente, abbiamo un po' di open mic, quindi adesso passo direttamente la parola a Gianluca e poi abbiamo un breve giro, Mario o Daniele per il Vox Days Milano e Francesco Vasco, ok, per il Cloud Conf, giusto? Sì. Ok, e poi direttamente partiamo con la presentazione. Ok? Vai.
Allora, visto che ci stanno tante altre persone che devono parlare, cerco di essere rapido. Solita domanda, chi è la prima volta che viene qua? Alzi la mano. Ok, tutti gli altri sanno cos'è sto posto, vero? Sì. Ok, piacere, mi chiamo Gianluca, faccio il programmatore, così mi trovate su internet e questo qui non è un coworking, ma è l'ufficio di un'azienda principalmente. Si chiama Mica Mai, ecco sì, non è un coworking, fa sviluppo in ambito web, Mica Mai, con varie tecnologie, qui ne abbiamo in realtà quasi tutte. Questo è l'ufficio di Mica Mai, ma voi potrete chiedere perché stiamo qua stasera, perché Mica Mai ha deciso, visto che la sera, il weekend, non usa il suo ufficio, di metterlo a disposizione alle community tech qui di Milano che ne hanno bisogno. Questa opera di supporto è seguita anche da Credimi, che non ha niente a che vedere con Mica Mai, se non per il fatto che io lavoro per Credimi e mi lascia dare una mano insieme a Mica Mai alle community, quindi grazie anche a Credimi. Perché famo sta cosa? Perché ci piace, e uso il plurale perché insieme a me a seguire le community ci sono anche Mara e Deborah di Mica Mai e Francesco di LinkMe, che è una piccola azienda che adesso è stata inglobata da Mica Mai. Perché davvero si fa sta cosa? Perché ci piace, davvero, sì. A me, Mara, Deborah e Francesco piace dare una mano e quindi andiamo avanti a fare così. Slide di ringraziamento agli organizzatori delle community perché tengono viva la scena tech qui a Milano e ancora di più ringraziamento a voi perché senza partecipanti si fa ben poco. Qualunque informazione vogliate in merito alle community, per favore non passate di qua durante il giorno, perché qui mica mai durante il giorno lavora. Potete però scrivere qui, scriveteci, soprattutto se avete magari una community e vi serve uno spazio tipo questo. Per i prossimi eventi invece c'è il blog.micamai.com su cui trovate un post per ogni prossimo evento. La marchettata, mi dicono di rifarla, io la rifaccio. Mica mai sta cercando sviluppatori front-end, quindi se siete interessati scrivete qui. Presentazione fatta, passo la parola al prossimo.
Ciao, sapete già di cosa vi stavo per parlare, credo. Stiamo ancora organizzando il Vox Days Milano. Ieri sera abbiamo fatto un altro meeting del program committee. Non dovrei dirlo io, però il programma è veramente bello quest'anno, quindi sono davvero contento di come stanno andando avanti le selezioni e manderò le email domani mattina agli speaker e mano a mano che approvano il talk li annunceremo. Siamo contenti di come vanno le cose, insomma, quindi dategli uno sguardo, fateci un po' di pubblicità se potete. Ancora meglio, lo ripeto, se avete la possibilità nel vostro datore di lavoro, in qualche altro modo, c'è qualcuno interessato a sponsorizzare, fate sapere me o Daniele. Che sto dimenticando? Niente, ok, basta. Grazie.
Vi rubo anch'io un minuto, Cloud Conf 2020, non so se qualcuno ha letto l'email, estremo qualche biglietto, vi dico soltanto cos'è, così almeno magari rimastate anche per i biglietti. È un evento sul cloud, non è soltanto Java, parla un po' di tutto, anche AWS, cioè parla più che altro di tecnologie, tra cui quelle per cui noi lavoriamo. Siamo già stati l'anno scorso come Jug, quest'anno ci torniamo anche come Vox. Se mi dici come hai fatto lo faccio a casa. Vabbè, lasciala così. Lasciala così, comunque si fa a Torino e siamo stati, è abbastanza grosso, interessante, forse uno di quelli non specifico, cioè non di Amazon o di Google, ma è abbastanza, cioè ci sono varie tecnologie e vari provider ed è quello che forse ci ha portato di mano qui in Soda. Se vi interessa, 19 marzo, ripasso la parola e chiudo qui.
Salve, buonasera a tutti, mi chiamo Mario Iotti, io vengo da Azul Systems come Simon, quindi brevemente solo perché adesso lascio l'esperto parlarvi. Quindi niente, sono il direttore commerciale di Azul, che praticamente lavoro coprendo tutta la regione di EMEA, e siamo qui appunto un po' per dedicare il nostro tempo, le nostre conoscenze, la nostra expertise a esperti come voi che siete interessati e lavorate col mondo Java. Quindi a noi piace sempre trattare direttamente con il pubblico, un po' per passare le nostre knowledge e poi magari anche a trovare qualche challenge che voi nel vostro giorno, con le vostre esperienze, giorno dopo giorno, con il vostro lavoro potete anche trovare. Quindi faremo c'è una prima presentazione e c'è una possibile seconda se c'è ancora tempo e se c'è voglia di coprirla. Quindi faremo la prima Java at Speed, how to build a better JVM. Quindi la cosa che a noi piace sempre di avere queste sessioni molto interattive, quindi se avete qualsiasi domanda che sia relazionata direttamente alle slide oppure una cosa personale di lavoro vostra, alzate la mano e siamo qua per voi praticamente, ok? Vi lascio a Simon e godetevi quest'ora di inglese puro British.
Okay, buonasera. That's it for the Italian. Okay, so as Mario said, what I'm going to talk about this evening is building a better JVM. Now, I am going to talk about what we do with Zing, our JVM. And don't worry, it's not going to be a marketing presentation. It's not going to be a sales presentation. I'm not trying to sell you on this. What I am going to do is explain to you what we do internally in the JVM to make it work in a better way. So you can understand what it is we've done to look at the way that the JVM performs and how we've changed it. So I'm going to reveal all the secrets of what it is we actually do. And so to start with, it's worth talking a little bit about what we mean by speed in the Java world. And to do this, I put together a graph which is what I expect in terms of the perfect performance for the JVM. Now, we're not talking here about the application code. We're talking about how the JVM runs your application and how it generates the necessary performance for that application. And the graph I came up with is fairly simple. So it looks like this. So the idea is that when you start your application, the JVM will deliver 100% of the possible performance straight away, instantly. And then it will execute at 100% of possible performance for the entire lifetime of the application, and then you stop it. So that's a very obvious thing to think, yeah, well, of course, that's what we want. We want 100% performance all the time. The problem is that if you look at the reality of how the JVM actually works, if we look at hotspots specifically, because that's the sort of OpenJDK way of doing things, the graph looks a bit different. So the graph looks like this, typically. So this is an execution of an application, and pretty much any application is going to look like this. So what we can do is we can sort of dig into this in a little bit more detail to understand what is actually happening when the JVM starts up and how you get to the performance that you have in terms of the JVM. So initially, you start the application and the JVM has to read the class files, which are your application code. Class files contain bytecodes, and bytecodes are the instructions of a virtual machine, hence Java virtual machine. The thing is that when the JVM starts executing those bytecodes, it does so in interpreted mode. That means that every bytecode that comes along, the JVM is going to look at it and say, how do I convert that into the necessary instructions or system calls that is required to make that work on the platform that it's running on? And this is the whole idea of Java's write once, run anywhere approach. Same set of bytecodes can work whether it's on an ARM processor running Linux or whether it's on a Windows processor on Intel. The problem is that the way that the JVM does that is it takes every bytecode independently, it interprets it, it converts it, and it does the same thing every time. So there's no performance improvement there. There's no caching, there's no cleverness going on. It simply takes a bytecode, converts it, executes it. Now, this is one of the reasons why, if you go way back to JDK 1.0, anybody here use JDK 1.0? Ah, good. At least somebody as old as me. So JDK 1.0, when it first came out, only did interpreting bytecodes. And that was one of the reasons that the JDK and Java specifically was criticized for being slow compared to C and C++ compiled code. So obviously the Java developers looked at that and they said, how can we improve the way that it works? And they looked around and they said, well, there's this existing technology and it's called just-in-time compilation. So what just-in-time compilation does is it looks at the application as it runs and it counts how many times a method is called. As the method is called lots of times, let's say you go into a loop and you start calling it repeatedly, a certain threshold will be reached and the JVM will say, ah, this method is a hotspot, hence the name of the virtual machine. It says that's a hotspot, so let's compile that code. Rather than interpreting all the bytecodes every time, let's take the code and compile it into native instructions. So we don't have to interpret it every time. The way that works is it uses a JIT compiler called C1. It used to be called the client compiler. And that's a compiler that's designed to compile code very, very quickly. But it doesn't apply lots of optimizations. So you generate code quickly, but it's not heavily optimized code. So the code will start to then perform a little bit better. But what will also happen is that as that code is running and the method gets called more times, profiling information will be collected about how that method is actually being used. When we get to another threshold where that method has been called enough times, the JVM will say, aha, this is a really hot method. Let's recompile it using a different JIT compiler. In this case, it uses C2, or what used to be called the server compiler, and that will apply a lot more optimizations. It will maximize all the things that it can do to improve the performance of the code. So we see a definite improvement in performance as methods get compiled. But we also see some drops in performance there. So there's dips as well as peaks. And those are due to what are called deoptimisations. And the reason for deoptimisations is that one of the techniques that C2 uses to optimize code as much as possible is speculative optimizations. And a speculative optimization is one where the compiler will say, this particular piece of code is executed this way all the time. So let's assume that in the future, it's going to do the same thing. Good example of that is if you have an if statement. So you've got two branches, true and false. And up until the point where you've compiled that code, you've only ever gone through the true branch. The compiler will assume that in the future, you'll still do the same thing. So you'll only go through the true branch and it will optimize based on that. Sometimes that assumption turns out to be wrong. So as we warm up, suddenly you'll go through the false branch for some reason, and the compiler and the JVM then has to say, we made a mistake, we have to throw away that code, de-optimize, and then recompile the code based on the fact that we need to have both branches supported. So eventually, having done all that C2 compilation and gradually compile all the methods that we need to, we reach a steady optimized state. So this is our 100% level of performance, the maximum that we can get once we compile all the methods that we need on a regular basis. So that's all good, but we still see some dips in performance. And those are due to a different thing. Those are due to garbage collection. That's the thing that obviously the JVM does. It looks after memory allocation, it looks after memory management for us. And most garbage collectors, in order to do that work safely, they pause application threads. We have stop the world pauses. When we look at the JVM, really we have challenges which are based on the fact that this is a managed runtime environment. And there are two distinct areas that affect the performance of the JVM, both of which we've seen in that graph. The first is the garbage collector. The garbage collector obviously does a lot of work for us. We don't have to remember to free up memory. We don't have to worry about allocating memory for specific objects. The problem with garbage collection in terms of the JVM is it's non-deterministic. We can't predict when the garbage collector will run. We can't predict how long the garbage collector is going to pause our application threads for. So we just have to rely on the fact that it's going to happen at some point and it's going to get in the way of our application. The second thing is this whole idea of using bytecodes rather than machine code. So we're not doing ahead of time compilation. We're using class files with bytecodes, and then depending on how we compile those bytecodes into native instructions, that has a big impact on the performance of our application, this whole warm-up phase that we see. So what if there was a better JVM, a better way of doing this? Well, funnily enough, because I'm here, there is an answer. It's called Zing. Essentially what we do at Azul is we've looked at the way that the JVM works. We've looked at these issues in terms of garbage collection. We've looked at these issues in terms of adaptive compilation. And we said, how can we change that to make it work in a better way and try and solve the problems of performance, if you like? Now, if we look at Zing as a JVM, what we do is we start with the same source code base as Hotspot. So we take the OpenJDK source code and then we modify it to use different techniques for both the process of garbage collection and some of the JIT compilation. But the important thing is that once we've made all of those changes and we've built our JVM, we then run all of the TCK tests on JVM and make sure it passes all of those tests. TCK is part of the Java specification. It's defined through the JSR under the JCP, and it's about 150,000 tests that you need to pass in order to call something Java. And we make sure, as I said, that we pass all of those tests. The thing about that is it means that our JVM is a direct drop-in replacement for other JVMs like Hotspot or J9. It means you don't have to change your code. You don't have to adapt it to using different techniques based on different system calls or different library calls. You don't have to recompile your code to use a different compiler to generate different bytecodes. You can simply take exactly the same application that you have, compiled in exactly the same way, and just run it on top of the Zing JVM rather than on another JVM. What we do in terms of changes, firstly, is to remove all of the existing garbage collectors that you get in Hotspot. So we take out the serial collector, the parallel collector, CMS, G1, Shenandoah, ZGC, all of the ones that are there. Just get rid of them all. And we replace it with one, which we call C4. And I'm going to explain a lot more about what that does in a moment. Now, one of the things about the way C4 works is that we only support it on Linux. And there's a reason for that, which is a thing called the Zing system tools, or the fact that we rely on certain specific system calls that are available through the Linux kernel. And again, I'll explain a little bit more about that in a moment. The second thing we do in terms of changing the JVM itself is we have replaced the C2 JIT compiler with one that we call Falcon. And again, I'll talk more about what we actually do with that as we go through the presentation. The third thing that we've done to improve performance is introduce a separate set of technologies called ReadyNow. So this actually makes a few changes to the JVM, but it's a little bit sort of outside of the JVM. And what this is about is eliminating the problem of warm-up of the application code. So going through that interpreted mode, C1 compile code, recompiling with C2, deoptimisations, and so on. So let's start by talking a little bit about the Zing system tools. if you look at Linux as an operating system, very popular, works very well, and it has a virtual memory system in it. The virtual memory system is responsible for mapping from physical pages of memory to the virtual address space of each process. And the design of that has been around for a long time. It works very well, but it's designed for general purpose applications because you have to design it to work with all sorts of different applications. The thing that we did when we were developing Zing was we looked at the way that the virtual memory system worked and we said, well, the JVM is a very specific application in terms of how it uses memory. You know, you allocate space for a heap, we need to manipulate that space, and rather than using the virtual memory system of Linux, why don't we replace that, or at least complement it, by putting a different way of manipulating memory into the kernel. And that's essentially what the Zing System Tools does. It puts a separate way of managing the memory alongside the virtual memory system of Linux. So when you boot the machine up, I mean, there's different ways of configuring it, but typically what we do is we grab 3/4 of the memory in the machine and allocate it to Zing under the Zing System Tools. You can change that if you want, but by default, we grab 3/4 of the memory. When the JVM runs, we're able to then manipulate memory and the page mapping in a way that's more optimized for how the JVM runs and how it uses memory. We're also able to do things like handing pages back when a JVM sort of has grown the heap but now has shrunk down and isn't using as much of the heap as it was. So we can return memory to the operating system and make it available for other instances of the JVM. We can do some other clever tricks with the ability to manipulate memory at that level. One of those is called contingency memory. If you have an application running on a JVM, and let's say, for example, you've allocated 8 GB as your heap space. Your application runs and it's all happy and everything's good. Then you start putting a heavier load on it and suddenly the heap space usage goes all the way up to 8 GB. If you try and allocate beyond 8 GB, you're going to get an out of memory error. And the JVM stops abruptly. And if it's a mission critical application, that's a kind of bad thing because it just stops. What we do is we have contingency memory that we hold back some memory to use. If we still have some, because obviously it's not infinite, and your application goes to try and allocate space beyond 8 GB, we'll actually let it do that. So it can go beyond the limit that it's set, and we'll allocate some more memory so it cannot generate an out of memory error. It can still carry on. We then run the garbage collector more frequently to try and bring that usage back down below the 8 GB limit. Plus, we'll send you a bunch of messages on the console and the log file to say, you did this and it's gone beyond 8 GB. You might want to think about expanding the heap space for this process. Now that in itself is very good and it's very useful, but we've had some issues, well not issues, but some people have said, well, you know, we'd rather have a version of Zing that doesn't have to install Zing System Tools in the kernel. You know, we don't have root access, we'd just like to be able to install the JVM and make it work. Specifically for things like microservices where you're deploying into a container, that's a much better way of doing things. You just want to put the JVM in the container and not worry about the host. So since August of last year, we've introduced a new version of Zing that doesn't install the Zing System Tools by default. And that way you can just use the Zing virtual machine in the same way you would another one. You don't have to install anything at the kernel level. That works fine for smaller heaps. If you go up to the idea of a larger heap where you've got 1 TB or more, then you do still need the Zing System Tools. And typically, I would imagine that if you're using microservices, you're not going to be using a heap of 1 TB. No, you laugh. It's funny because I was talking to a customer last week, and I said, well, of course, you know, we have this idea of 1 TB limit, and microservices, I'm sure, will be less than 1 TB. They went, no, we have microservices that use 1 TB heaps. I'm like, microservice. The clue is in the name. But anyway. So yeah, if it's 1 TB or above, then you still need the Zing System Tools. Okay, let's talk a little bit about garbage. Now, in the JVM, in Hotspot, there are a number of different garbage collectors available. So you've got the parallel collector, which is good for throughput. You've got CMS, which was designed as a more, let's say, responsive, low latency type of garbage collector, but as of JDK 14 is gone. There is not going to be a CMS in JDK 14. G1 was the replacement for CMS, which it used a similar sort of technique, but had the idea of regions rather than fixed areas of memory, so it was an improvement in that way. Shenandoah has been around for a little while. People like Alexei Shiplev are working on that. It's not in production yet. It's getting very close, I know. And ZGC, which is a more recent development from Oracle, which is very much an experimental project. It's still using a single generation heap, things like that. Again, not in production. The important thing about, well, all of the commercial collectors that you can get at the moment and use in production is that all of them at some point will say, okay, in the old generation, we have too much fragmentation, we don't have enough free space, we have to do a full compacting collection. And at that point, it will do that full compacting collection, and that's where you see some significant garbage collection pauses. So if you're sort of, running something, you might see, hundreds of millisecond pauses, you might see some second pauses. If you're really unlucky, you might see pauses that last almost a minute. What's the longest garbage collection pause you can think of? Maybe a few minutes? The largest garbage collection pause I've come across was a customer that I spoke to a couple of years ago in the US who had a garbage collection pause of 1.5 days. Yeah, and I must admit, when I was talking to them, I said, 1.5 days? And I said, how do you know it's even doing garbage collection after a few hours? And they said, no, we have JMX instrumentation. We can see that garbage collection is happening. It still works. And then I said, well, isn't it just easier to stop the process and restart it? And they said, no, it actually takes more than 1.5 days to reload all the data and process it. So we're actually better off running the garbage collection for 1.5 days. Sorry? So the heap was, I think it was about 8 terabytes that they were using. And
was occupied by the single linked list, probably.
yes. Well, it was actually a credit card company that was doing fraud detection, and that was the thing that they were using it for. And I must admit that when I talked to them, I said, we can actually do pauseless garbage collection. They're like, really? We can get rid of 1.5 day pause? Yeah, that was an easy sale, that was. Yes, so the pause times that you get with that kind of garbage collection is proportional to the size of the heap. It's actually not proportional to the amount of data in the heap. It's the size of the heap, so that's quite significant. Okay, so let's talk about what we do to make that work in a different way and eliminate the problems of garbage collection. So we have a garbage collector called C4, and C4 stands for the Continuous Concurrent Compacting Collector. And essentially that tells you what it does. So the first thing is it's continuous. It means that it runs all the time with your application code. So it's always running in the background. Second thing is it's concurrent. That's very important because we do it concurrently with your application threads. So we don't pause your application threads to do work. We actually run at the same time. Third thing that's very important is it is a compacting collector, meaning we relocate objects within the heap to eliminate fragmentation and to make the objects contiguous in memory. And obviously it collects garbage, so we eliminate the objects that are no longer required. In terms of the basics of C4, the first thing is that it is a generational collector, meaning that we have a young generation and an old generation. The reason for that is that there is this thing called the weak generational hypothesis. And that says that if you look at a typical application, in fact, almost every application, most of the objects that you allocate in your application are only used for a very, very short amount of time. So literally 98% of your objects will become garbage before another megabyte of heap has been allocated. 98% of your objects will be garbage within a few hundred milliseconds of when they've been allocated. So what we want to do is have a young generation so that we can eliminate a lot of objects quickly and not place a load on the old generation. That's used in a lot of different garbage collectors. In fact, pretty much all garbage collectors use generational heap space. There are a couple that use single generations, but most of the ones that people use have 2 generations. We use the same algorithm in both young and the old generation. That's different to most people. If you look at Hotspot, Hotspot will use a simple pointer bumping algorithm for the young generation, and then it'll use a more complex one for the old generation. But we use the same algorithm on both young and old. And the reason for that is because, as I said, the fact that we can eliminate a lot of garbage in the young generation means we don't place a load on the old generation. So it's actually more efficient doing it that way. The key thing, as I said, is we do not have a stop the world pause in terms of compacting fallback. In fact, we don't have stop the world pauses at all. It is a truly pauseless garbage collector. And in terms of the algorithm that we use, we have 3 phases to that. So it is mark, relocate, and remap. And all of those can operate in parallel. So we can have multiple threads handling all 3 of those phases. Okay, how can we do concurrent garbage collection? Because if you look at the way that other garbage collectors work, they pause application threads in order to do garbage collection work. And the reason they do that is so that they can relocate objects within the heap and do it safely. So the application threads are not changing the objects as they're being moved. In order for us to do that safely and move objects while the application code is running, we have a thing called a loaded value barrier. And this is essentially a read barrier, which means that every time you access an object, we will intercept that and we will test certain things. This allows us to enforce 2 rules on what the JVM does and how the garbage collector works. First thing that we enforce is that if we're in the marking phase of the garbage collector, whenever you get a reference to an object in the application code, we guarantee that it has been marked as live data, so it will not be garbage collected. The second thing that we enforce and guarantee is that if we're in either the remapping or the relocating phase, then the reference you get to an object will always be the correct one, so that there's no issue of you updating an object that has been moved and the change that you make to that object getting lost because we've then changed where the object is. As I said, this allows us to do both concurrent marking and concurrent relocation. The thing that some people say is, well, hang on, if you intercept every read to an object, we do a lot of that, so doesn't that degrade performance by placing an overhead on every access of the object? And the answer to that is, well, yes and no. The reason I say yes is because clearly we have to do something. How we do that is by using some bits in the object header. We use bits in the object header to indicate that we know which phase of the garbage collection we're in, but we need to know certain information about the state of that object header in relation to marking or in relation to relocation. Because we use bits, we can do a test and jump. We test the bit to see if it's set. If it's not, we jump to a handler because we need to do some work related to garbage collection. If it is set, we can just continue and we can provide the reference to the application and it can carry on. Most of the time, we don't need to use the handler. So most of the time, we'll just pass through and test the bit and carry on. By doing that, the effective overhead is 2 instructions. It's test and jump, which when you boil that down into the micro operations at the processor level, it's a single micro operation. The overhead is therefore roughly 1 nanosecond per object reference. Now, sure, if you're using lots of object references, that starts to add up. But what we've done is we've analyzed that, and you'll find that if you could write an application that only used L1 cache, so it never went outside the L1 cache of the processor, you would see a degradation in performance due to our loaded value barrier of somewhere around 0.5 to 5%. But remember, that's only if you use L1 cache. The moment you go to L2, L3 cache, or main memory, the effect of those memory accesses is far more significant than the overhead of our test and jump. So for pretty much any normal application, the overhead of our loaded value barrier is insignificant. Okay, so how does this actually work in practice? When we want to run the garbage collector, we need to do a marking phase. The marking phase is going to go through and it's going to ensure that all the objects that we have access to from our application are marked as live, so we don't garbage collect them. To do that, we take the same basic approach as many other algorithms. We create a root set. The root set is a list of all the objects that you have accessible directly from your application. We scan the stack, we look at the registers, we look at static variables, and we build up a list of the object references that you have. Now, many of those objects will have references to other objects, and those objects will reference other objects and so on. We therefore need to trace the full graph of object references and mark all of them as valid. So our garbage collection threads will start on the root set, and they will mark the first object as being valid, as used data. So we set the bit in the object header to indicate that that's a valid object. Then we need to trace from that to other object references, and we mark the bit in the object header to say that that object is valid, and that object is valid, and that object is valid. The root set consists of independent object references, so we can actually apply multiple threads to that and do the work in parallel. So there's no problem with making that phase completely parallel. Our application threads are running concurrently, meaning that they're still doing work and they're still accessing objects. So at some point, the application thread needs to access an object. So we intercept the object header reference and we do our test and jump. If we find that that particular object has not been marked, then we jump to our handler. And our handler will do the work of indicating that that object is still valid by setting the bit. The important thing here is that we're effectively doing a very small amount of garbage collection work in the context of the application thread. Now, that object is likely going to have references to other objects that need to be traced. But we don't want to do that from our handler, because technically that's an unbounded task and could take a long time. To get around that problem, what we do is we say, okay, well, we can use that reference because we've guaranteed it's marked, but we'll then pass that object to the garbage collection threads, make it part of the root set, and let the garbage collection threads trace the object references there. Because, of course, even if that application then uses an object that's referenced from that, which isn't marked and hasn't been marked by the garbage collector yet, we'll go through the same test and jump to our handler, and mark it before it's returned to the application thread. The key point here is that every object reference that the application thread gets is guaranteed to be marked and won't be garbage collected. So we enforce the first rule that we have. Next thing we need to do is relocation. We need to take our objects which are spread around through the heap, which have gaps between them, and we need to move those to make them contiguous. We need to eliminate the fragmentation and the space between them. We can do that fairly easily, because what we can do is we can say we have 5 objects in our heap here, A, B, C, D, E. And we can calculate new positions for those in empty space in our heap, so that A moves to A prime, B moves to B prime, and so on. That's effectively compaction, by copying those objects from one place to another. We do that as the application threads are running. But to do it safely, obviously we put a lock around that application or that move, copy. Because that way we can't have any problem with the application trying to access the object while we're actually doing the copy. Now that would introduce a pause, and it does indeed introduce a pause, but remember we're copying objects individually, and most objects are very small, which means the time it takes to copy an object from one part of the heap to another is going to be very small as well. So the overhead in terms of pause times, negligible in most cases. Having calculated our new position, having done the copies from one place to another, we also record all the information about where those objects have been relocated to. And we do that in a side table. So you have a side table that says A has been moved to A prime, B has been moved to B prime, and so on. Now there's a very important reason for using a side table. One of the techniques that are used by other collectors is called a Brooks forwarding pointer. A Brooks forwarding pointer basically has a pointer within the object header that points to the object. And in fact, it's within the object, and sometimes it'll point back to the object itself if it hasn't been relocated, and if it's been relocated, the pointer points to where the new object is. The reason we use a side table is another benefit that we get from doing our own virtual memory management. And that's what's called quick release. So we have a mapping between our virtual address space of the heap and our physical pages that we have in memory. In order to do garbage collection, we only require one free page of memory per garbage collection thread. And that means that we can, let's say you have 8 garbage collection threads. We can collect a full 8 terabyte heap with only 8 free pages of memory. The reason we can do that is because when we've said, okay, A and B have been moved to this page, so we use our free page of physical memory and we can copy the first 2 objects into that free page. At that point, even though the address space of where A and B is still technically valid, we are managing the mapping between physical and virtual address space. So we know that those objects are never going to be referenced again. We never need what's in that memory. The information is in the side table. We haven't used a Brooks forwarding pointer, so there's no need to go back to those objects. That means that we can steal the physical page from underneath the virtual page. Even though it's technically still valid, we can take the physical page away and eliminate the data that's in there and use it as the next page that we're going to then copy objects to in order to compact our heap. We can also then grab another page and use that. And that could also be used in terms of allocating new objects in the young generation. But technically what we're doing is hand over hand collection. So we grab pages and we do quick release. And that's a nice way of improving the efficiency of how the garbage collector works as well. Next, having relocated our objects, we need to do a remapping phase. And this is where we need to take the information in the side table that says that A has been moved to A prime and so on, and we need to update the information in the object headers. So our garbage collection threads will come along and they will start working through the side table and say, okay, we need to update object A. So we'll take the information, we'll change the reference in object header A to the new place where that object is, and then we'll set the bit in the object header to indicate that this object has been updated and is the correct information. Similarly, we can have multiple threads running on that and we can update information through there. The application threads are running concurrently. So at some point, we need to reference an object. This will then do our test and jump again. So at this point, we test the bit and we say, aha, this bit has not been set to indicate that this object needs to be updated. At that point, the handler will then, again, do part of the garbage collection work in the context of the application thread, go to the side table, get the information, update the object header, set the bit, and then return the object reference to the application thread. So again, we guarantee that even though we've moved the object in the heap, the application threads are still running concurrently, it will get the right reference to where that object now is. So you get completely safe relocation of objects whilst application threads are running. So C4 is a truly pauseless collector. And if you look at the sort of typical worst case latency that we get, out of the box, as in we're not doing any tuning, we simply run Zing with your application, you'll get about 10 milliseconds as the worst latency for garbage collection. If we do a bit of tuning on that, we've got a few parameters that we can set, we can typically get that down to less than 1 millisecond, worst case latency. The nice thing about this is also that the way this algorithm works is it gives a very consistent latency profile, meaning that it doesn't matter how you change certain parameters, the latency will stay the same. And we can scale basically from 512 megabytes, that's the smallest heap space that we recommend, all the way up to 8 terabytes of heap space. And the latency will not change regardless of how big you make the heap. We do have some customers who are currently asking us to increase the maximum heap space to beyond 8 gigabytes. And we're in a kind of a bizarre situation because if you think about it, the object header is the thing that allows us to reference the size of the heap. And we need 1 bit in the object header to double the size of the heap that we can reference. And we can't find 1 bit in order to reference 8 terabytes of heap, which I kind of find weird. But anyway, we're still hunting for that 1 bit. Somewhere we'll find it. Doesn't matter, also allocation rate. We can handle very high allocation rates. 20 gigabytes a second is perfectly normal for us. And so long as you have sufficient heap space, we will keep up with that. Duration of running the JVM, you can run it for weeks, you can run it for months, doesn't matter. You don't have to restart the JVM in order to clear things out. It will just keep going indefinitely. Memory fragmentation, low profile, doesn't make any difference to us because we compact, fragmentation isn't an issue. We actually compact as we go along. Okay, let's talk a little bit about GC tuning. And this is one of those things that if you look at other garbage collectors, people spend a lot of time and a lot of effort tuning the way that the garbage collector works to try and reduce the pauses that you get with garbage collection. The reason for this is that if you look at the hotspot VM, there are lots of command line flags that you can set in order to change the way that the garbage collector works. Obviously, you've got lots of different types of garbage collector, and then there are many parameters that you can set for how each of those collectors works. So here's a couple of examples. And these are both real-world examples of how customers that we worked with have set up their JVM to work with a garbage collector. Now, we don't need to go into all the details of what they've done here, but I'm going to highlight one particular thing, which is that both of them have set the survivor ratio. One set the survivor ratio to be 128. The other set the survivor ratio to be 2. What's the right answer? Is it 2? Is it 128? Is it 64, 32, 17? Maybe not 17. Probably not a good number. But the issue is that how do you figure out what value to set that to? Now, I'm sure lots of people here have done tuning of garbage collection. And you know that a lot of the time it's trial and error. So you try changing it, you see whether it works better. If it doesn't work better, you change it the other way and see what happens. That's okay if you've only got one parameter to change. But there are lots of these. And so you end up pretty much with an n-dimensional space of trying to figure out all these different values and work out what's the best set of values to give you optimum garbage collection pauses. So let's look at the equivalent set of parameters that we would set in terms of tuning Zing to give us the best possible performance. That's it. We basically just set the heap size. Now, I agree. We literally have a handful of other parameters that we can set. But to start off with, that's all we do. We set the heap size and we let the algorithm do what it does. And realistically, the only thing that we do when we're working with a customer initially to determine the best arrangement is say, okay, start off with a heap size. Does your application run without running out of heap? If it does, okay, let's bring the heap size down, so we reduce the amount of resources we use. Okay, if it just about works there, we'll kind of take it up a bit more, give us a bit of headroom, and that's it. That's essentially all we do. We say, set the heap size, and off you go. Okay, now how can I prove to you that this works? What we've done is we've created a small open source tool called JHiccup. And JHiccup is designed to measure the latency of everything below your application. So it doesn't look at the latency of your application code and how quickly it can process transactions. It looks at what's the latency of the JVM, the operating system, and the hardware underneath it. And to do that, what we do is we add an extra thread alongside your application in the same JVM. That thread doesn't interact with your application code. So you don't have to change your code. We don't have to do anything to make it work with that. And to avoid the problem of Heisenberg's uncertainty principle, we don't really do very much in that thread. We literally spend most of our time asleep. When we start, we go to sleep for 1 millisecond. When that thread wakes up, we look at the system clock and we say we expected to wake up 1 millisecond later. When did we actually wake up? If you started and you went to sleep and a garbage collection pause kicked in, it was 20 milliseconds, our thread will wake up 20 milliseconds later than it expected to, so we can record that delta, record it in a log file, generate some histograms, and then we can produce some nice pretty graphs. Now, pretty graphs are very good. So this is the kind of thing that we can generate. This is an Elasticsearch example. On the left, we've got Hotspot. On the right, we've got Zing. And this is running on a moderate heap. This is 128 gigabytes of heap. If you look at the left-hand side in Hotspot, what you're seeing there is a very typical type of garbage collection profile. You've got lots of small spikes. And those are spikes that are generated by minor garbage collections on the young generation. And then you've got two bigger spikes, which are latency that's generated by old generation garbage collection. So very typical profile for stop the world pauses associated with young and old generations. Now remember that high is bad. So if we look at Hotspot, you look at that and you go, kind of looks rather random, doesn't it? I mean, it's got some big spikes there, but it's quite random in terms of what it's doing. But I have been very deliberate here in misleading you because I have used different scales on the graph. So if you look at the Hotspot side of things, that's using 0 to 8,000 milliseconds, which is 8 seconds. So most of the small spikes are around the half a second range, and the big spikes are sort of 5 to 6 seconds in size. On the Zing side, I've scaled it 0 to 80 milliseconds. So it's a bit different. If I scale those graphs the same, now you see what Zing does, because it essentially eliminates all of the problems of garbage collection. It just flatlines the latency, and you can see that garbage collection just disappears. There is no issue in terms of latency there. That's 128 gigabyte heap. It's being collected concurrently with the application threads so that the application itself is experiencing no noticeable latency from the point of view of garbage collection. Give you a different example. I've only got two. This is Hadoop, and this is running, and this time I have scaled it on the same graph. So this is running on a Hadoop with a 5-second range. So y-axis is 5 seconds. And again, you can see that Hadoop is doing quite a lot of, spikes there, and those are around half a second, but you've got something going up to, 4.5 seconds there. Zing, pretty much flatline. So then I thought, okay, let's rescale it and see what's really going on. And if we scale it on 500 milliseconds, you're still really not seeing much happening in terms of the Zing JVM. We really have to go down to 50 milliseconds before we see some activity. And there, what we'll see is, okay, on the Zing side, there's a couple of spikes that are going beyond 10 milliseconds. But remember that what we're measuring here is latency that's associated with JVM and everything below it. So some of those latency spikes, not things that we can control. The operating system is doing context switching and stuff like that. So we can eliminate a lot of all the problem of garbage collection, but we can't eliminate what the operating system is doing below us. Okay, so that's garbage collection.
Yes, I have one question. Given that C4 is generational, still use something like a card marking table in order to check?
Absolutely.
Those,
Yes, because you have to have the cross-generational references. So we do use a card marking for cross-generational references.
And in that case, if you have a workload that is not generational, like that kind of workload, how it behaves?
We don't find a problem with that. I mean, obviously there's more things that we have to do underneath, but we can cope with that. So we were still able to deal with situations like that, so that we can still eliminate the issues of latency associated with garbage collection.
Would be nice to configure it with just one generation sometime, maybe.
I think we try. I'd have to go back and ask Gil, but I'm pretty sure we tried that originally, but we decided that it actually works better with 2 generations. I mean, we've been doing this, we've been working on this algorithm for the better part of 10 years. So I'm pretty sure that we've tried the idea of 1 generation. Okay, so that was garbage collection. Now let's talk about what we've done in terms of improving JIT compilation. And this is, like I said, what we call Falcon. What we did was we said, okay, changing C1 isn't really going to buy us any improvement in performance, because C1 is just about compiling code quickly. Even if you compile the code more quickly, it doesn't really make that much difference. C2 is where you're going to get the most improvement, because if you can generate more heavily optimized code, you get better long-term overall performance. And we looked around and we found that there's this really nice open source project called LLVM. LLVM's been around for a long time, and it's supported by a lot of significant companies who are in the space of developing chip architectures, compilers, and things like that. So there's people like NVIDIA, people like Intel, Microsoft, Apple, all the kind of people you'd expect to see are working on that project. It's really primarily designed as a static compiler for C, C++ type code, and generating from an intermediate representation the binaries for a particular platform. But what we said was, okay, we can use that, because we can use that as the back end of our JIT compiler. And we integrated it into the JVM so that it would work with things like the garbage compiler, the garbage collector. It would work with other parts of the JVM. And then, being good open source citizens, we contributed all that code back to the LLVM project, so that if anybody else wanted to use it as a JIT, they could without doing too much work. What this does is allow us to get better performance from the code that's generated by the JIT compiler. We can do better things in terms of the intrinsics that are generated. We can do better in terms of inlining, and we have fewer excludes from the compiler. So very much this is a replacement for the C2 way of doing things. So if we look at a simple example here, this is just a loop that is going to take an array of integers and it's going to add them up. Now, if you give that to any compiler today, the compiler is going to identify that the best way of optimizing that is to use vector operations. Vector operation uses a wide register, and it loads up a number of elements from your array into that wide register so that you can apply a single operation on multiple data at the same time. So it's single instruction, multiple data. Very good way of improving the efficiency of numerically intensive application code. So that's fine. Compiler will do that, all good. However, if you make the code a little bit more complicated and you introduce the idea of conditional statements there, then it becomes hard for a compiler to recognize that this can still be optimized by using vector operations. So if we look at a simple example here, that piece of code, and we show that in terms of what the C2 JIT compiler does. Now, don't worry about all the individual instructions there, but the key thing to get here is what the C2 JIT compiler has done in terms of optimization is very basic. It's essentially done loop unrolling, and it said, okay, let's do 2 elements of our array per iteration of the loop. So it's doubled the number of elements it can process per iteration. It's not a great optimization, but it does a little bit to improve performance. If we look at Falcon, the code for exactly the same piece of Java code looks very different. Actually looks like there's more instructions there, which technically there are. But what we're seeing here is, firstly, that Falcon is using loop unrolling and doing 4 elements per iteration of that loop. But it's also identifying it as code that can use a vector operation. And we're using, on this particular processor, we're using AVX2, which is a 256-bit wide register. The net effect of that is by doing 4 elements per iteration and vector operations, we can do 32 elements per iteration of the loop, compared to 2 that you get with C2. Numerically intensive operations, very good, so we get much better performance there. And the really nice thing about Falcon and using LLVM is, firstly, that LLVM is a very modular design. So it's clean, it's easy to work with, and so adding new features to it is a very straightforward thing to do. I won't say simple, it's very straightforward in terms of adding new features. The other advantage that we get is we do a refresh from the project every once in a while, and we pick up a whole load of features that people like Apple and Microsoft and NVIDIA have added to the compiler. So suddenly we get like, oh, good, all this works much better than we thought it was, which is great for us because we take advantage of open source. Right, last thing in terms of the features that we've been working on is ReadyNow. And the idea here is, as we've seen with our graph, is that we have the idea of application warm-up. I'm sure you're all familiar with this, is that the application starts running slowly and then gradually gets better in terms of its performance. The problem with that is that every time you start the application, it goes through the same process. So it has to go from interpreted to C1, compiled, profiling, then recompiling with C2, and then you finally get to your better performance. So every time you start the application, it does the same thing. That's really not very good. So ReadyNow is about letting your application run, start it up, get it running so it's at a fully warmed up level, and then we take a profile of your running application. Now, most people will say, oh, isn't it just a case of, why can't we just take a snapshot of the running application, and then we want to start it again, we just reload that snapshot and off you go. It's a nice idea, but it doesn't work. And there's a couple of reasons for that, which is that, one, if you look at the JVM definition, the way it's specified, you can't simply do that. There's certain things you have to do when the JVM starts up related to classes and class loading. The other thing is, if you just took a snapshot of a running application, you'd end up with data that might be, let's say, for example, the date is encoded into your information, and then you load that, and funnily enough, the date's not the same date it is when you took the snapshot. So you can't just reload all the running code. What we do is we take a profile which includes the important information. So it's all the classes which are currently loaded, all the classes which are currently initialized, and that isn't necessarily the same set of classes, all the profiling data that's been collected by the code that's running as C1 before it was handed to the C2 or Falcon JIT compiler, and most importantly, all the speculative optimisations which turned out to be false assumptions, where we had to throw away the code and then recompile it. So we collect all this information, and the important thing about that is we can collect that information over a much longer time if we want to. You can let your application run for a couple of minutes, you could let it run for a couple of hours, a couple of weeks if you want to, until you're happy with the performance, and then take a profile. Similarly, you can take profiles at different times. So if you want a Monday morning profile or a Friday afternoon profile, you can do that. Once we've got that profile, when we start the application, we use that information. So the JVM will say, aha, we have a profile. Load all the classes that we can from that list. Initialize all the classes we can from that list. Then take the methods that we know we have to compile, pass them to the Falcon JIT compiler, along with profiling information and that speculative optimization information where it failed, so we don't make the same mistake. Let the Falcon JIT compiler compile the code before we start running our application. So when we get to the main entry point, in your public static void main, you've literally got about 98% of the performance that you would have had when the profile was collected. We can't quite get to 100%. You need typically 1 to 2 transactions to run through your code to just kind of kickstart it into the same level of performance you had before. But essentially, when you start your main, you've got almost the same level of performance you had when you took your snapshot. So again, if we look at a sort of simple graph from a customer application, orange is before you use ReadyNow, so you see this warm-up phase where you've got high latency because of compilation and so on. You've got ups and downs because of deoptimisations. If you use ReadyNow, blue line flat lines against the latency, so you don't have the problems of that whole warm-up thing. Now, that's all well and good, but we have a little bit of an issue there, because what we're now doing is a whole lot of work before your application actually starts. So there's all this compilation that has to happen before you get to the main entry point and actually start running your code. So we thought, how can we improve that? Right. So I said, you can't just take a snapshot of your code and then reload it. So what we thought we'd do is take a snapshot of our code and then reload it. We can do it, but it's a little bit more complicated than that. So what happens is that we can, if we look at a graph, so this is the simplified graph without ReadyNow. We have our warm-up slope. If we use ReadyNow, then, okay, we have a much steeper graph in terms of getting up to maximum performance, but we've got this blank spot where the application's not doing anything whilst we do the class loading, initialization, and compilation. So compile stashing is based on how the compiler works. And if you look at Falcon inside, what you've got is the bytecodes that are being converted into the intermediate representation that's used by LLVM. Those get passed to the LLVM compiler, and then LLVM has to ask some questions of the JVM. There are certain things it needs to know about how that method was used so that it can make decisions about how to optimize the code. So it sends queries to the VM through callbacks and then gets responses in terms of the answers to those queries. Based on that information, the intermediate representation and the queries to the VM, it will generate optimized code and pass that back as a set of machine instructions that can be executed. If you look at how that works in a bit more detail, you find that the compiler is fully deterministic. And by that, we mean that if you take the same set of initial intermediate representation, so if you haven't recompiled your method, so you've got the same method code, and you've got the same set of queries and responses, meaning that you have the same profile associated with that method, then you guarantee that the code that's generated by Falcon will always be the same. So given the same set of inputs, you always get the same output. We can use that so that when we do our compilation part, where we take our intermediate representation, we pass it to LLVM, it does queries, gets responses, and then generates machine code. We put the compile stash, which is all the compiled code in between there, and so long as we get a match in terms of the profile, we can just reuse the code. Now, obviously, things like the date and so on, we take care of that. But in terms of the actual compiled code, we can reuse that without having to recompile it. And that's a really big thing in terms of improvement of performance, because without compile stashing, like I say, you get this sort of blank spot where the application does nothing. With compile stashing, we can reduce that amount of time by up to 80%, and we can reduce the CPU load as the application starts by up to 60% because we're not doing anywhere near as much compilation. So long as you don't, change your code between, in fact, changing your code between runs will invalidate the ReadyNow profile anyway. But so long as you've got a fairly sort of stable run of your application, then you can really take advantage of that. So just to sort of summarize what we've done then, essentially, if we take the initial optimum graph that I showed where we've got 100% all the time, and overlay that with the reality that we get with a typical JVM implementation, we've solved all of those problems, almost all of those problems. So the gaps in terms of garbage collection, C4 eliminates those. By using Falcon, we can actually raise the maximum level of performance by improving the optimization of the code that we generate. And then by using ReadyNow and compile stashing, we can push that envelope all the way out and get a much steeper graph in terms of the startup time associated with the application and getting it to run on the JVM. So the way that we describe Zing is to start fast, to go faster, and to stay fast. And the idea is that it is a simple replacement for other JVMs. You don't have to recompile code, you don't have to change your code, you don't have to use anything different. And the idea is that we encourage people to try it out, run it with your application, use JHiccup, and that's how we get these nice comparative graphs so that you run on exactly the same machine, same workload, and see what the difference is. Generate a nice graph where you see it completely go flat. I was talking to somebody today and they were saying that they'd been doing an analysis of Zing and they kind of generated the graph and it came out flat and they went, "We've broken it, it doesn't work." And they had to change the scale until they finally found that, yeah, there was some activity there. I was like, oh, it is working. It's like, that's the kind of customer we really like. Yeah, so you can try it free for 30 days. You can do it, download it, and run it on your machine and give it a go. So, grazie mille. If anybody has questions, I'm very happy to take those.
Well, one is maybe stupid, but honestly, day-to-day work actually still happens, and when I apply optimization to C++ code, it breaks the code. And you have to fall back to the initial version because the code is running in any way. This thing happens also in just-in-time compilation. How do you avoid this?
I mean, I certainly would say that I don't know of any of our customers that have complained about using Falcon, for example, and finding that the code doesn't work.
Well, I was talking in general, not about really about the just-in-time compilation. It's thinking about what happens in real life. When I use LLVM as a compiler, that one when I use compilation, a strong optimization breaks the binary, and that's the behavior. The behavior breaks the behavior.
Like I say, I've not come across any of our customers who've complained about that, where they've used Falcon and found that it's changed the behavior functionally of their application. Obviously, it will change the behavior in terms of the performance profile, but I haven't found anybody that said, well, the code doesn't work in the same way that it should have done. If we come across anything like that, that's clearly a bug and we fix it. Yeah. One thing I would say kind of related to that is that we were working with one of the Apache projects. I can't remember which one it was. It was one of the kind of lesser known ones. And they were doing some performance analysis on their code in Java. And they have a big section where they're doing some very heavy I/O. And they thought, okay, to see how that works compared to the sort of Java code, they rewrote it in C++ to generate very heavily optimized code. When they compared the code that had been generated from their native C++ code with what we were generating with Falcon, it was pretty much identical. which was funny enough, well, because they were using LLVM, you see, so it was using the same back end of the compiler, so we were able to go, well, yeah, you get the same thing. It's like, ooh, that's good. It actually gave them a 50% improvement in performance just by switching from Hotspot to Falcon, which was nice. Good.
Have you changed something in LLVM in order to make it aware of things like save point or?
Oh yes, yeah. I mean, we've absolutely had to do that. So as you say, it needs to be aware of things like safe points. It needs to be aware of things like the garbage collector. So integrating LLVM into the JVM as a JIT compiler versus a static compiler was quite a lot of work. The fact that we've now done that is good because we've done that and it's all kind of completed. So our effort now is on improving the way that it works rather than just making it work.
So in theory, if anyone wants to leverage on
Yep.
this kind of
Yep.
improvement, oh, nice.
Yeah, like I say, we contributed everything we did back to the LLVM project. So other people, if they want to take LLVM now and use it as the back end of a JIT compiler, they can just take all the work we did and use that.
The Julia language uses LLVM as a JIT, but I don't think it does profiling. It's just kind of like doing ahead of time.
Right, yeah.
Also WebAssembly. I relies strongly on LLVM. Yeah.
More like a cultural question about what do you think it's been missing from the open source JVM community that can reach these impressive results? I mean, we are on a totally different scale here. I mean, we've got lots of latency and zero latency, basically.
Yeah.
So it's incredible to me, to be honest. I mean, we have plenty of good developers.
Yeah.
In most of our companies, I mean, developing for the OpenJDK, and we cannot really reach. I mean, I know that you work. I mean, you sell this, so I mean, if you can answer this.
Yeah. Oh no. I mean, there's a couple of things I say about that. I know. So Gil Tene, who's our real CTO, unlike deputy CTO, he's our real CTO, and I know when I talked to him about this, he said, so about 10 years ago, they sort of came up with this algorithm based on work that other people had done in terms of garbage collection. And so they put it all together and they tried it and they figured out how to make it work. And they kind of looked at it and sort of went, why has nobody ever done this before? This kind of thing, And I mean, the reality is that now Oracle have ZGC, and ZGC uses some very similar techniques. Yeah, it's a little bit different. I mean, they use a read barrier, so they're using the same basic approach that we do with our loaded value barrier. They do still have stop the world pauses. They're fairly short, but they do have stop the world pauses, which we don't have. The thing I would say about ZGC is that people I've spoken to who've tried it, they've said that they get fairly good, they get good results from it in terms of latency, but it crashes a lot. And essentially, if you look at the development of ZGC, there's two guys in Stockholm who are working on it, and they kind of did that in their spare time initially because they said we can write a better garbage collector. They worked for Oracle, and they said we can write a better garbage collector. So they put together this algorithm and did it. Oracle have open sourced it, but I know from the people I've spoken to at Oracle, I used to work for Oracle, that they're not putting a huge amount of development effort into it. And certainly when I was working at Oracle, I remember talking to the product management people for Java, and I was talking about Azul at the time. I said to them, there's Azul, they've got this great Zing JVM, it's got, low latency and everything. Why don't we buy them? And the product manager said, yeah, it's not really what we're into. We're looking at, sort of like the server-side stuff, and, it wasn't their target market, so they weren't interested in buying Azul at that time. So yeah, I mean, it's certainly, things are changing in terms of, like I said, ZGC and things like that. So there is some work going on in terms of that. And then you've got Shenandoah as well, which is another different approach in terms of solving the garbage collection problem. That's designed to work with large heaps. Well, Alexei tells me not to say that. But it's typically using larger heaps. And it's designed for low latency. The thing is that with both Shenandoah and ZGC, they are single generation. So they don't use multi-generations at the moment. And again, there's a strong argument for using multi-generation heaps.
What about
Aha. Well, yeah, running inside a container. As I said, that works completely fine. The tricky bit used to be installing the Zing system tools. But now, as long as you're using a small heap, less than 1 terabyte, in your container, then you can use ZVM without the need for the Zing system tools, which means you just install it in your Docker image and you can run it in exactly the same way as you would any other JVM. So that will work without any problem.
And we should expect a similar performance.
Yeah. Oh yes, absolutely, yeah. Yeah, the only thing you don't get without the Zing system tools is things like the contingency memory. So if you do get to your maximum heap size, you're thrown out of memory error. But
Because it would be difficult to manage that against the other containers.
yes, yeah. I mean, you can do it because if you install the Zing system tools on the host, you can treat each JVM and you'll still get the benefits of the contingency memory within those. But it makes the setup a little bit harder. But if you just want to deploy containers, you can do that without any problem. The way it works with not using Zing system tools is we use some of the more modern system calls that Linux, well, I say more modern, I mean, when I looked at it, it's actually quite a long time ago that they introduced this. But it allows you to essentially map an area of memory that you can use. It's like a memory map file, but it doesn't use a file as backing store. So you've literally got an area of memory that you can map, and then we manipulate that in order to make the JVM work in a better way.
I had a question about the microservices, well, the Docker world.
Mm-hmm.
It was before when you were talking about the optimization that we can store and reuse without compile each time.
Mm-hmm.
How this thing works when, I mean...
In a container.
I suppose that during the run, the optimization were stored locally, but we were in a Docker machine somewhere in the cloud.
Right. Yeah. So the thing with using ReadyNow inside a container, the sort of runtime part is very easy because all you're doing is adding an extra file into your container image and then setting the appropriate command line flag so that when you start the JVM in the container, it uses that profile. The tricky bit, if you like, is generating the profile. So you can either do it from within your container and then just copy the file out, or you can do it just running your application outside the container, generate the profile once you've warmed up the application, and then put that into the container. So it'll work either way, but you have to generate the profile in order to make it work.
So, well, I have a container who is running since a couple of days, a week.
Mm-hmm.
I connect to the container,
Yep.
copy the optimization or the...
Exactly. Yeah.
That's the way.
Yeah.
Okay.
Yeah. So you could basically, like, if you like, log into your operating system on your container, tell the JVM to drop or generate a profile, and then just copy that out of the container and then duplicate it for whichever containers you want to use it on.
It would be a good idea. Oh, well, we could also share a mount point between the
Yeah. Also, yeah.
containers
Yeah.
to don't lose the optimization.
Yeah. Essentially, it's just a file. So how you make that available, there's many different ways of doing that.
Yeah. Okay.
There's something that I didn't understand memory contingency. So you said that when you finish memory,
Mm-hmm.
the heap, you don't throw any other memory exception because you manage to allocate more memory.
Yeah.
But to do that, you have any kind of swap system where you put the whole memory? I mean, where do you find the memory?
Right.
That's the question.
Yeah.
I think it's a great time. It's like you can
Yeah. So the way that it works, when you boot the machine up, like I said, we grab 3/4 of physical memory, and we make that. Let's say we are using Zing system tools. So when the machine boots, we grab 3/4 of the physical memory, and part of that, which again is configurable, we will reserve as contingency memory. So let's say we take 10% of that. So if we're on a 128 gigabyte machine, what's that, 96 gigabytes we're grabbing initially, and we'll keep, let's say, 10 gigabytes back as contingency memory, just for sake of argument. That means that when you run an application and you've got an 8 gigabyte heap, we've still got 10 gigabytes that we can use as contingency. You get to your 8 gigabytes and you try and allocate beyond that, rather than throwing it out of memory error, we'll just allocate more memory to the heap for that JVM. So it can then carry on allocating space. And then, as I say, we'll run the garbage collector more frequently to try and bring it back below the 8 gigabyte limit that's been set. Does that make sense?
In Docker world, you have a waste time concept.
Well, yeah, if you're running in a container, it gets a little bit more complicated because, of course, you've got the C group limitation on how much memory is allocated to the container.
You stay out of the memory for, let's say, 1 minute, 2 minutes, and if you go beyond, you have an out of memory.
Yeah, ultimately you'll get, if you just keep allocating forever, so if you have a memory leak and you keep allocating forever, eventually you'll get an out of memory error because we don't have infinite memory available. So eventually you will get an out of memory error. But the idea is that if we have contingency memory available, will allow you to go beyond that 8 gigabyte limit. But yes, if you're working within a container, then you could bump into the C group limit rather than the issue of contingency memory.
Well, the question was, I don't explain myself very clearly. The idea, or the question was, if you use a rest time also inside the Azure JVM. So if I can set a rest time of, let's say, 1 minute.
No, we don't have a time limitation. No. No.
Okay.
No, it's purely based on memory size.
I have a couple of questions actually about use cases, if I may ask, for as much as I may ask. So it's like one, so during the presentation of today, you've shown how Zing then solves some of the problems where normally you could say, I cannot write Java basically for real-time applications. It doesn't solve all of them. So for instance, context switching would still be like not theoretically for real-time, and this does not go into that direction. But I was wondering if you've seen actually cases where customers or anybody is saying, oh, actually we thought that we need a real time, but actually seeing that that you're doing with Zing, it actually matched what was our SLAs or our expectation.
Yeah. Oh yeah, absolutely. I mean, that's one of the kind of key areas that we sell into is people who want not hard real time, where you've got absolute guarantees on latency, but they're looking for soft real time, where they want to get the response times down to, a fairly predictable level. So we can say, okay, we can do it in less than 10 milliseconds of latency. But clearly, if there's something that happens at the operating system level, context switching or whatever, that forces that latency up, there's nothing we can do about that. And the customer has to accept that limitation. So it's definitely soft real time rather than hard real time. And a lot of the use cases that we have are quite happy to accept that kind of thing, where we give a quite predictable, from the JVM point of view, we have a very predictable response time.
And the other question that somehow is still about use cases, like something that looks really interesting to me is like you've shown how you're using LLVM as sort of the backend for that. And actually LLVM is using other sort of like communities of languages to actually just go to, for example, to WebAssembly and so on. So I was wondering if some communities or customers were looking into that for sort of like a gateway for like, more from like WASM, so WebAssembly and stuff like that. So like the opposite direction where sort of like the rest of the world seems to be going that wants to take their JavaScript and put it in Node.js just to have it on the back end. So I was curious to know if you could see some spark at the light of the end of the tunnel or something like that.
I must admit, I've not seen anybody kind of trying to do that yet.
Well, just a question.
Yeah, no, I've not seen anybody try to do that.
You can be the first.
Which kind of profiling tools are useful? Can be used with Azure?
Right. Yeah, so tooling perspective, we developed our own tool, which is called ZVision, which allows you to basically interact with the JVM, and you can see what's going on in terms of, the usual things of threads and garbage collection, heap usage, and so on, things like that. What we've done more recently is because Oracle open sourced Flight Recorder and Mission Control, we've now integrated Flight Recorder into ZVM, and you can then use Mission Control to monitor a Zing virtual machine in the same way you can hotspot. And we've obviously adapted it to give the different types of information that you get based on the fact we've got C4 rather than CMS or G1 type thing.
So you have implemented the async get code trace inside the...
Yes.
Okay.
Yeah, we basically copied the flight recorder code, which is in the JVM. So a lot of the information is gathered. We just use the flight recorder code so we can expose that outside of the JVM.
You just compile the code from bytecode to netcode once, or you use the code using the implementation of LLVM to recompile it later and have better performance on the netcode?
So if I understand what you're asking about like static compilation AOT.
Yes, and using the instrumentation of the LLVM to have the runtime information and recompile the
Right.
code for better code.
Yeah, see, this is an interesting discussion because obviously approach that different people are taking is looking at AOT rather than JIT compilation. So if you look at things like Graal and if you look at things like Quarkus, that relies on AOT because then that gives you very fast startup time versus using JIT, which gives you a warm-up time and then you optimize based on that. So AOT is very good for giving you fast startup time. But the problem with AOT from the perspective of overall performance is the level of performance you get is lower because the optimizations that you can apply from a JIT compiler are much better than you can get with AOT. Simple things like method inlining, you can't do as aggressively with ahead of time compilation. Java is a dynamic language from the point of view of class loading. So when you compile code before you run it, you don't necessarily know which method is going to be called at runtime because somebody could use a class loader and replace it. So you can't necessarily inline all the methods that you could if you're doing JIT compilation, because JIT compilation, you know exactly which classes are loaded, which methods are being called, so you can do more aggressive method inlining. The other thing that you can't do with ahead of time compilation that you can do with JIT compiling is speculative optimizations. And what we found is that more than half of the performance improvements we get from JIT compilation is down to speculative optimizations. So that's one of the big sort of downsides of AOT is that you can't do all the optimizations you can with JIT. But what you're saying, which is a very good idea, is run AOT, so you generate native code, get the fast startup time associated with that, and then profile, and then recompile using, say, Falcon and LLVM to generate more heavily optimized code with all the advantages. That's something we haven't quite got to yet. So it's certainly something we're looking at, but at the moment, our sort of focus is on, or has been, on using ReadyNow to eliminate the problems of warm-up. Obviously, we've still got some issues there in terms of the time it takes to get to running the application, even though using the code, the compile stash is better from that point of view. But yeah, we're definitely looking at how to do both AOT and JIT compiling combined to give the maximum possible performance, yeah. Okay, I was going to say, how are we doing for time? Yeah, not too bad.
Okay, thank you very much.
Thank you.